time history analysis. So we know distribution of motion for the dynamic systems can be written like this. Where M is your mass matrix, C is your dynamic matrix, A is your frequency matrix, and F is your motion function, which is dynamic in nature. You will observe that we can identify mass matrix because we know how the density is varying or what is the density of particular material. For this case, for density is 785 kg per meter cube. Okay, so we can identify the mass matrix. Similarly, for Stokes matrix also, we know what is the Young modulus, and we know what is the cross section property is. The things we know, we can calculate the Stokes matrix. But you observe that we do not have any generally everyday model. So what we used to do, we used to assume damping matrix your function of A0M plus A1K. So here what we are assuming, the damping matrix is basically damping matrix is the linear combination of mass and status matrix along with some coefficient. Now here you can say that there is no logic, to consider the damping matrix like this. It can be in other form, but for our mathematical convenience, we are assuming damping matrix and the combination of A0A plus A1K. Now here main problem is how to find A0 and A1. So we assume that the matrix will be your linear combination of this term. Okay. Now here there is two unknown A0 A1. Now A0 and A1 can be calculated from this formula. In correlate our model damping factor or frequency. When we can calculate our model damping factor with the frequency in this formula. Okay. And here if we concentrate in this formula, here if you see this formula and if you try to plot it in graphical representation, you can observe that if the frequency is very low, in that time your damping matrix is dominated by your A0 term. First one, damping matrix is dominated by the your model damping factor, or other way damping matrix is dominated by your first term, that is related to your mass. So you can say this is mass proportional damping matrix. If your frequency is very high, in that case, the damping matrix is dominated by the second term. If frequency is high, obviously this term, first term, will be very low. Now your damping factor, model damping factor, in other way, damping matrix is dominated by your mass proportional constant. So your stiffness proportional constant. So you can say the damping matrix is stiffness proportional. So graphically we can represent it here. But for this case, what we are going to do, we are going to consider both C matrix with the linear combination of A0M plus A1K. Now our job is to find how we can identify the A0 and A1. Now here you just see there is two unknown A0 and A1. So basically we need two equations to get this two unknown. Okay. Now here what we are going to consider, we are going to consider now if we have a problem, if we have a structure, okay, and you can identify the frequencies and the damping, okay, then it is very easy to identify A0 and A1. It is very easy to identify A0 and A1. So here what we are going to do, here we will write how much modal damping factor is coming for the first mode, and we will write what the frequency of the first mode. Okay, and again we'll write what is the frequency, what is the modal damping factor, and what is the corresponding frequency is there. Okay, now we have two equation and we have two unknown. We can solve it and we can get it. So if we have two equation and two unknown, what we can do, we can write these things in matrix form, and we can get the inverse of it, and we can solve your problem, and you can identify A0 and A1. Okay. Here I'll show you how we can identify. What I did, I written a small MATLAB code to get our A0 and A1. Here you can see. Here you can see J1. Here I have assumed 0.25 is modal damping factor. First mode is 0.25. Okay. J1 modal damping factor for the first mode is 2.5. J2 0.1. Now problem will arise if you have experimental data. If you have all the experimental data, okay, if you have omega and xi, you can easily identify A0 and A1. Now, if you do not have your experimental data, if you do not have frequencies, and if you do not have modal damping factor, then what to do? In such case, you can perform defined element analysis. What you can do, you can model your physical systems. For our case, it is cantilever beam. I can model it, and I can perform modal analysis and identify what is the frequency are coming. Okay. What are the frequencies are coming. Okay. Now once I identify frequency, then what we can do, we can assume some damping factor. We will observe in the engineering practice, we assume 5% damping, some cases we use 2% damping. So in that way, in that sense, we can assume some damping factor for your system. So here, what I assume 0.25 damping factor for the first mode and 0.1 damping factor for the second mode. Okay. And next, what we did, I just put the value here, and I just calculated the A0 and A1. So here, what I observed for our case, we have assumed a cantilever beam where length is 1 meter, process in dimension of 50 mm plus 10 mm. 10 mm is the thickness, and we have fixed end here. And property we have considered 200 GPa as your Young modulus and Poisson ratio 0.33. So we solve this problem. We'll observe that mode shapes, Hertz mode shape is coming frequency of 8.15 Hertz, and second mode you will observe that is coming nearly 40 point something, but that is not coming in our XY plane. Okay, that was our other plane. So we do not consider that mode. Okay, we did not consider that mode. Third mode was basically coming to 51.04 Hertz. Okay. I just consider that is the second mode, and I put the value here. Okay, I put the value here, and I solve it. Okay, so I'll show you how I solve it in MATLAB. Here you just see. So modal damping factor for the first mode, I assume 0.25. If you have experimental data, you can the data here. J2 is 0.1, omega 1 8.15 Hertz, and omega 2 consider quantified input function. So that is basically in our XY plane. So our mode shape was reflected in our Y direction. Okay. Now what I did, I just fill the coefficient matrix. Just fill this matrix here. Just fill this matrix here. And thereafter I will take the inverse of that matrix and multiply that. Once I run it, observe our value is coming, coefficient value is coming 8.9 and 0.9. So this is the way you have to calculate the damping coefficient A0 and A1. Okay. Now, if you do a real testing, in that case, you will be able to find the frequencies as well as your corresponding modal damping values. Okay. So what you can do, you can directly put the value here. Okay, and you can calculate the coefficient. Okay. Now here, if we see that A0 and A1 coefficient must be positive value. Okay, you will observe that in some cases, different combination of omega and xi can give you a negative coefficient. A0 and A1 may be negative. You have to ignore that part. Okay. So what you can do, you can consider the average value of the frequencies and average value of damping value. And another state, you can consider other frequency value and take the average of it, and also can find the average value of the damping. Like that, you also can calculate A0 and A1. So what will happen, you will observe that in an average sense, your response will match. So this is the way basically you have to calculate your Rayleigh damping coefficient. I hope you get some idea. Thank you.